Okay, welcome everyone to another episode of GPU Mode. Today, I'm really honored to have Tianqi Chen, who is really one of the founders of the field of ML systems. I think someone in chat noticed that you have 101,261 citations. I don't know if you know this.
Oh yeah.
Yes, but yeah, I mean, for context, just as Tianqi is a bit more humble in his presentation, but if you've been in AI long enough, you've likely used Tianqi's work without even knowing it. Whether if you converted pointers from from one tensor library to another, if you've used an ML compiler, odds are you've basically been exposed to Tianqi's ideas. So yeah, I mean, today the topic is going to be on TVM FFI. This is a newer library Tianqi's been working on. If you've been paying attention to the NVIDIA kernel competitions, you might have already noticed how a lot of the top submitters are using a TVM FFI. And hopefully Tianqi can tell us a bit more about what the project is. So if you have any questions to him, please feel free to ask in chat. Thank you.
Sounds great. Thanks, Mark, for the introduction, and thanks everyone for having me here. It's really great to be in GPU Mode community. Today, I'm going to talk about TVM FFI, this open ABI and FFI convention for machine learning systems. And it's part of work that we've been doing in the past 1 year that we think is really important to enable good interoperabilities among domain-specific languages, compilers, runtimes, and libraries. So to begin with, I think we are kind of in a very exciting area of building machine learning systems, right? So on one hand, we start to say a lot of cases the relevant of GPU mode are the DSL and compiler and kernels, right? We have DSL and kernels that allows us to be able to write different kind of kernels in different languages. And I think there's the trend is kind of still continuing. There's nonstop, right? We also start to see a lot of libraries like CUDN, FlashInfer, and many DSL written libraries as well to start to be able to drive a lot of the applications there. And also, a lot of those libraries now start to be able to written by agents, right? So agents are another kind of important trend where we want to be able to agents are able to write both, log, CUDA-C, PTX even, or some of the DSL kernels. And one interesting thing is that in a lot of cases, a lot of those libraries are built by different people, right? So even DSLs themselves can be developed by different compiler developers. And also, they kind of need to interact with many components. Like, for example, we could have one of the mandatory case today is, they have to work with PyTorch and Python environment. Right? So that's one potential use case. But also, in a lot of cases, there are still a lot of, especially for some of the automotive and other robotics deployment, we kind of need to move towards environment that, that do not come with Python. And there are other cases where, we still have graph executors and graph runtimes, especially on some of the edge environment, where we want to be able to kind of have those graph executor like TensorRT to be able to make use of those. So this creates kind of this many-to-many connections here. And also it brings this interoperability challenge, right? So in a sense that for any of the environment, like for example, today, any DSLs we developed, the first question we want to ask, how do we run it in Python, right? Because kind of Python is the first class citizen. But also a lot of these, if you want your DSL library or be able to say ship to robotics or bring it to a self-driving car, then you want to think about, how do we support non-Python environment? Also, in cases where, if you are building your own execution engine and compilers, or even in today, if you build specialized LM engines, you will start to think about, how do my engine start to interact with those? And this thing in the middle is kind of like this kind of big challenge where today, what we do is we start to have dedicated bring up effort, right? So we'll have, for example, for any DSLs, we want to say, hey, let's bring up PyTorch to support that. Maybe, depending on the production team may want JAX. So we kind of need a separate team to be able to bring JAX support for the DSLs. And for kernel agents, it's the same story because we can have AI agents writing great kernels, but we do want to ship them to the product of interest. For example, if I want to ship my AI generated kernel to self-driving car, then I would need to kind of make sure, I need to wrap that sufficiently, right? And also, for example, if it's a Python DSL kernels like QDSL or Thailand or other kernels, we want to be able to make sure that I can try to get the core of that and also ship that into an environment of my production that may not come with Python. Like maybe I want to use Rust to call them, maybe I want to write a C++ program to call them. So this all brings kind of interoperability challenges that we're facing today, and it's kind of getting worse, right? And this is one of the, I think it's a byproduct of the golden age, in a sense that we are looking at a lot of the innovations on multiple fronts, and then it kind of creates interesting challenges on how do those components interact with each other in here. So I also want to give a few example scenarios that we can think about when thinking about these interoperability challenges, right? So the first example is, first of all, how do we ship kernel libraries? This is like a specific case when we find when we build Flash Info library, for example, at NVIDIA, because we kind of need to be able to ship Flash Info to a lot of platforms. Like we want to be able to ship it to PyTorch, which is the most important citizens, right? So we want to be able to make sure Flash Info runs well on VLM, SGLang, and other environments. But we also started getting requests on, hey, can you bring Flash Info onto, say, TensorRT Automotive, which is like a platform where you can try to run TensorRTs on a self-driving car environment, or on the edge robotics environment that do not come with PyTorch direct Python support. We also get like a fun request, like, hey, I really like Rust. Seems like an interesting language. Right? Can I try that? Can I call Flash Info library from Rust? But also, while we are shipping Flash Info libraries, we also start to see requests of, hey, we need to ship it across Python versions. Like, we want to ship it across Python 3.9, 3.10. More recently, we have threaded Pythons involved. Like some of those are partly resolved by some of the ABI3 solutions from Python, and more recently PyTorch also have like stable ABI, which is a great direction that moving towards that. But still, we would like to have a solution that reasonably minimal, be able to ship across Python versions, and also ship across framework versions. Like we get requests or, hey, we really want to bring up Flash Info for PyTorch, but also there is this JAX-based framework that we want to support. So in the meantime, of course, we also want better PyTorch support. Right? We want to be able to make sure that we can directly pass in PyTorch streams, while if you are doing PyTorch graph capture, CUDA graph kind of works out of the box. It's kind of a mandatory thing that we kind of want to think about. So we do get this question of how can we ship kernel libraries such that ideally we don't want to ship specific kernel libraries for each of those solutions. Ideally, we want to ship one version of libraries so that it can work across all those scenarios. So that's like one of the concrete motivation problem that kind of motivated this particular FFI project.
So Tianqi, I had two questions actually. If we go back to the previous slide, yes. So this is like, maybe could you give the audience like a sense of like why this Python version matter for people?
That's a great point. Sorry, I missed that. So for to give everybody a background, right? So normally, if you write pure Python .py, it doesn't matter, right? So it's going to work out of box on all those Python versions. But in most of the cases, when we are shipping libraries, especially kernel libraries, we kind of need to compile the code. And when we compile the code, they need to interact with what we call Python ABI, which is a set of standard libraries that Python define through language C, right? So effectively, all the kernel library speaks the lowest level language called C, and you kind of need to interact with them on C. However, the Python ABI or the API that Python exposes across versions can be different. On Python, they have this, I think starting 3.8, they started this effort called stable ABI, which is a subset of Python API that if you target that, it's going to be stable. However, more recently, when we introduced threaded version of Python, for example, the threaded Python do not guarantee ABI stability. So kind of we still need to ship across versions, right? Similarly, if my library, for example, links against libtorch, different version of libtorch may change their own internal APIs. As a result, we may need to kind of like change our binaries, right? When we change libtorch. That problem has been greatly alleviated by recent stable PyTorch ABI effort, right? So I think it's Mark brings a great point in a sense that ABI is not a very common thing that people bring up. It's kind of like a hidden thing behind the thing, but it's kind of a very important factor when you start to ship your software across versions. Yeah. And today's topic is exactly about, how do we think about ABI in a minimum way? Yeah.
Thank you, Tianqi. This is like the briefest explanation I've heard of the problem, so thank you. So my second question is like, what does it mean to sort of support CUDA graphs out of the box? Like at least like within PyTorch, like people might be familiar with CUDA graphs at a much higher level, which is like you just sort of explicitly do the graph capture relay, or you're using a compiler.
Yep.
So what do kernel DSL authors have to think about that the rest of us don't?
Yeah, so normally like CUDA graph support should be out of box, right? But on the other hand, it really depends on when you launch a kernel. The key is you don't want to do extra things. For example, sometimes a kernel library might do something like a malloc, or in certain cases it might do a kind of like a string synchronization implicitly, right? So those are the things that can mess up CUDA graph, right? So ideally, for example, when PyTorch start to run kernels, it kind of makes the assumption of, you are going to capture on all your operations are going to launch on the particular CUDA graph stream, right? So for example, if your kernel library relies on assumption that I'm going to have my side stream that's not be recognizable by PyTorch, then that's something that will not support CUDA graph out of box, for example. So effectively, it's mainly interoperability with PyTorch's native environment stream, if that makes sense. Yeah,
it does. Yeah, I mean, so stream, like here, basically stream and CUDA graph support really are the sort of the two.
Really are the same thing. Yeah.
Okay.
Cool. So that's like the issues of kernel libraries. Of course, DSL is like it's another very important thing. And myself have been working quite a lot in ML compilers. I also have a very good passion for DSLs. We built some of the machine learning compiler in past. I'm still building some of the DSL variant, right? So really, we are in a golden age of shipping DSLs. I think it's a great thing in a sense that, I think the bar of building DSL are reasonably lowered thanks to some of the recent infrastructures, as well as some of the kind of ongoing momentum, right? We all start to see that it's very important to kind of be able to specialize and really get the best kernel out. However, when we start to ship DSLs, it's really very interesting to ask that what does it take to build a DSL? I know that not everybody have to build a kernel DSL, but it's really interesting to think about like do a thought exercise, right? So say if you want to build a new DSLs, what you need to do? There are, of course, the non-surprising part. I think this is a non-surprising part. Like, hey, if I want to build a DSL that targets Blackwell, I will need to either generate either CUDA-C, NVVM, if you are using like LVMIRs, or you can directly emit ptext, right? And then somehow you try to generate a cubing, you bundle that, and then in your DSLs you need to bring abstraction so that you do all the right tricks. Like you want to be able to invoke TCGs, running TMAs, making use of strap broadcaster, right? So these are all the fun part, and a lot of cases, when we're writing kernels, these are all the things we want to learn about, right? However, there's another part that usually that's equally important, but also get overlooked. That's the host side. That there's the question of once we have the cubing generated, how do we launch a kernel, right? So specifically, I think that's also come back to a topic of ABIs. When we have DSLs that generates low-level code generator, usually it's kind of exposes in a very low-level primitive. You don't really necessarily out-of-box get direct Python access, right, to your thing. So you want to think about, say, if I have a kernel, how do I expose my JIT kernel to Python? That's like a just exposure question, right? So and also there's also a question about how do we support ahead of time compilation. So normally in DSLs, if you do like a add cute kernels, it's more like a just-in-time compilation, right? Just-in-time compiles and expose it to your runtime environment. However, say if I want to ship it to self-driving car robots, right? So then in that case, ideally I want to be able to write the code in Python. I want to export that, and then I want to be able to just link that in my C++ or Rust application, right? Without worrying about the Python runtime at all. So that's the question of how do I ship ahead of time compilation. There's also a question of how do I work with PyTorch, right? That's another question that I can think about. The most naive approach or the most obvious approach that one can think about is, say if I have a DSOs, it generates something that's very low level. At least I can try to use a binding framework like PyBind or NanoBind to be able to bind a particular function to my output, right? However, different DSOs may have different function signatures. Like, I have one function that takes in one tensor, I have another function that takes in two tensors, three tensors. It's kind of very tedious to kind of really manually kind of bind each kind of function that we want. So, and also, these are all the questions on the host side. Effectively, a host means that all the kind of like a preparation logic you need to be able to get your data from PyTorch data structures, kind of marshal them onto a format that your DSL recognize, called CUDA launch, and launch the kernel. And that's kind of a very important part that's usually get overlooked. And even if it's not getting overlooked, like for example, initially when we build QDSOs, a host side kind of have quite a big of overhead. Mainly because a lot of Python DSLs also need to involve with Python. As soon as they start to involve Python, as we will see in a later part of the talk, they kind of like the time kind of start to accumulating very fast, right? And the GPU is getting faster, so the whole side is really something that's very interesting to think about. And so if I build a DSL that compiles the function that takes three parameters, ideally, right, we want several things. We want you want F, right, to be able to take Torch tensor out of box. Of course, right? You want to build a DSL. Ideally, it should work with PyTorch out of box. You want it to be minimal overhead. Like ideally, the host side should not get in the way, right? So if the GPU launch takes 2 microseconds, your host side should definitely takes less than 2 microseconds. Otherwise, it's gonna get in the way. There are other extra nice needs. For example, if there are some errors in my DSLs, like either CUDA error or sometimes maybe my parameter do not meet my demands, ideally I should not do like a exit one, right? For example, if you have a C language, the easiest way to handle errors you just do exit one and you abort your program. But that's going to crash your Python interpreter. You don't want to do that. You want to be able to throw the right kind of exception to Python, right? You also want to be able to support maybe some form of more compact data structures. Like what if you want to pass in tuples of tensors? You want to be able to call the Python callbacks if necessary. And also ideally, right, we want to be able to support other frameworks, AOT support. All these things are also problem DSLs developers need to consider in here. Or ideally, DSL will be able to solve all those problems so that while you are writing DSL, you don't have to worry about those problems anymore. And finally, a kernel agent, I think, is also a very interesting part because effectively you can view each kernel agent as their own DSL compiler, right? So because they are generating something that kind of exposes a function signatures, you have all the same demands. Like you want to make sure all those generated function works with PyTorch. You want to be able to bundle them and ship them to your deployment environment. And each kernel language, each kernel agent kind of either need to use a common framework or build their own framework to solve this problem. So these are all common scenarios that we're thinking about. And one of the key things that we're thinking about at heart, right, the key challenge at heart are actually this problem of ABI, application binary interface. It's more like how languages talk to each other at the native level, right? Languages talk to each other at more like a bare metal level, and the ABI defines when you build a function, how data are stored and how they get parsed across each other. For example, say I have a PyTorch tensor, and there's another array framework called QPy, which also kind of can allow you to run n-dimensional array operations on CUDA platform. Today, you cannot directly pass a Torch tensor to QPy ND array. This is because Torch tensor will have its own specific in-memory layout to talk about here's the data, here's the strides, here's the GPU pointer, right? And QPy might decide to arrange it in a different way, so you can not directly passing your your data structure, tensor data structure from Torch to QPy. That's because there's the application binary interface mismatch. It's not an API, because API kind of is more like a API level, right? The ABI is like effectively, if you look into if you do a call dump of your core stack at a certain time point, how data is being stored in memory, right? And can you so the question ideally, right, you want to be able to directly pass a law pointer of that particular data to another framework, and another framework is able to directly recognize it, right? So that's like the ABI problem. Another thing that's very interesting that I think is not commonly recognized, this the FFI challenge or foreign function interface challenge. Because previously, mostly when we do programming, we always think about one language, right? We always think about, hey, everything stay in one language, so that most of the functions we write, you kind of like being exposed to the same language. However, the very nature of machine learning kind of mandates some form of cross-language interoperabilities, right? So the simple example is Python and C++ or Rust extension today. And as a matter of fact, every DSO are on their own mini languages, because when you write a code generator of DSOs, they kind of need to generate something that can only be accessed in a very raw form. And then you start to build binding support to be able to bind that onto the environment. So each DSO can be viewed as their own language and need kind of runtime and binding support to different frameworks. So that's the world today, right? And I think there are like two different possibilities forward. The first way is maybe let's try to develop one unified programming language so that we can try to put all the programs and application into that single language. And that where, you can kind of interopt very naturally. That's kind of one possible path, and there are some attempts on that direction. Our take is that diversity is really fundamental and here to stay. So we kind of want to think about, what is another alternative way we can try to kind of alleviate or try to help the ecosystem, right? So that's we want to focus on what we call sustainable interoperability. Specifically, we want to make sure that the call across DSOs and functions as a first class concern. But of course, there's a trade-off, right? So because it's not possible to kind of like have any language call into another programming languages arbitrarily, because otherwise the design complexity is going to blow up, because different programming languages may have their own design considerations on how they lay data in certain ways and so on. So we are not trying to solve that for a general problem. Instead, we specifically focus on ML AI system needs, where we know that the calling patterns are reasonably clear. Like we need to have functions that can take tensors or maybe composite of tensors across each other. Like sometimes maybe you have strings, integers. Like we can enumerate kind of like a possible calling patterns in here, and as a result, we will be able to. And also want to focus on ABI, which means that instead of trying to say here is a very complicated framework that everybody use, we want to think about what is the lowest level representation that everybody can talk to, right? So that they will be able to, ideally, we want to be able to directly take a pointer and you will be able to kind of call into that if necessary. So that's the ABI and FFI challenge. And that motivates us to kind of like propose TVM FFI. So this is not a framework, it's not a compiler. It's just a minimal standard ABI convention in its first place, right? So it's kind of being made independent from specific compiler framework or deep learning framework like PyTorch, JAX, and so on. And it's meant to be universal across compilers. So it's kind of started from this Apache TVM compiler project, but then we kind of isolated out into a minimal independent libraries that's less than 1 megabytes and can be further trimmed down. And today is kind of a minimal ABI standard. And the idea is that we want to be able to define what does it mean for us to expose a function that machine learning system call into each other. The key elements of TVM FFI contains several things, right? First of all, I want to define how do we kind of like exchange tensor data, like how do we take a PyTorch tensors and get it passed to my DSL function. And in there, we're kind of just reusing existing protocol called DLPAC, which we also kind of co-developed it, and being widely adopted by communities like PyTorch, JAX, and so on, that defines how tensors are being stored in memory. We also have what we call compact value and function ABI that I'm going to explain in the next few slides on what does it mean to represent a function, right, of common data types in machine learning. And this will going to expose a stable CABI that can be directly used by compilers and runtimes. And because we are kind of working at a C level, almost every kind of DSO languages will be able to directly talk to C. So it kind of enables a lot of like a direct cross-language bindings. And we also have like, good error handling API so that we can kind of propagate error correctly. And of course, the most important thing is we want to have first-class Python and PyTorch support while being able to work seamlessly with non-Python environment when there's a need. right? So that's like at a high level, the design goal of TVM FFI. And it's really meant to be a kind of open standard that we use to be able to represent this calling convention across languages for machine learning system. So to give a rough example of how we do it through flash infer, the idea is that the flash infer library is going to, in this case, we are kind of doing a JITting function of certain CUDA template. So in this case, this is a flash infer sampling function. You don't need to look at the specific code, but a high-level idea is that we have a micron that allows us to be able to expose existing CUDA function onto a TVM FFI symbol, which I'm going to explain in detail what does it mean. And then it's going to give me a flash infer sample.so. So this is a API, is a platform agnostic binaries that do not, actually this don't depend on Python or Torch. So it does not have dependencies on Python or Torch, and support general set of environment. And it does have a dependency on this libtvmfi.so. So this is a minimal runtime library that's around 1 megabytes because we include debug symbol and so on. It can be trimmed. You can even just bundle it into a C+ runtime, right? So it's kind of dependent on that library, mainly for error propagation and a few other kind of environment management needs. So once we have this .so libraries, what you should be able to do is you can pick up these libraries in different environments. For example, I can pick it up in Python. In this case, you can use TVM FFI load module to be able to load in that module, and you will be able to directly call this sample function by passing in torch tensor in here. You can also run it in different functions, right? Different environments. For example, this is a C++ example where you can also similarly load the module from C++. You get a function, and you will be able to directly call the function in C++. And the idea is that this workflow, right? This workflow of having a framework called DSO produce TVM FFI compatible binaries, and this particular binary is able to runnable onto different environments. This workflow is reusable by other compiler and coding agents. So I can just replace, for example, flash infer here with queued DSOs, and the same workflow on the right-hand side is going to stay the same, right? So that's like the general high-level workflow example. And of course, when we are building this, we're building first-class PyTorch support. So for example, when we have this add one CUDA in here, I can allocate torch tensors. You will be able to directly pass torch tensors to TVM FFI functions through the DLPAC format. We heavily optimize this Python interface so that the rough API overhead from a PyTorch interface in this case is roughly 0.4 seconds. So for reference, even if you are doing nothing and just write, say, an empty PyBind code, you will take at least 0.1 microsecond to be able to invoke a function. So it's like really close to speed of light. It's very versatile. So this particular program not only works with PyTorch, but you can, for example, replace the torch tensor by QPyTensor. It's also going to work because a lot of the array frameworks are compatible with the DLPAC. The error propagation is built in box. So we will show in the future QDSO examples on how we can leverage the same mechanism to propagate, throw the right kind of Python exception to the caller, right? And also, we do handle streams out of box. So in this case, when you do a with torch.streams, within the API, we have function to be able to obtain the stream from the environment. And as a result, this particular kernel is going to launch on a write torch stream. So you can use CUDA graph capture or other ways to do it, right? So, and another important thing about this add one CUDA is that this particular function do not have dependencies on Python or Torch. So it's a minimum function in here. And it can be loaded in other environments like JAX callback, C++, and Rust for different purposes. So now we talk about the.
So Chen, just a question. So this overhead, is it something you just eat once, or is it like on every call?
It is on every call. It is on every call. Yeah, and so we can even get it down further to about 0.3 or 0.2. But by this point, it doesn't matter too much because most of the kernel overhead is about 1 microsecond. So as long as you can hide below 1 microsecond, like you're not going to observe the impact in here. Yeah.
Oh, I see.
And yeah, go ahead.
But I guess, could you give me some color into like what happens basically during this
So
time? Yeah.
so effectively, when we are calling this add one CUDA, right? So what you need to do is you kind of need to be able to take these Python values and quickly reinterpret them onto this low-level ABI convention, and we write a hybrid Python and Python C++ based binding to do a very quick, vtable style dispatch. And minimize the overhead significantly. So and of course, this also thanks to with collaborations PyTorch community as well. So we had a recent fast DLPAC C conversion extension API being merged into PyTorch, so that this kind of exchange can be made out of box without having to. So for earlier version of Torch, we have a kind of minimum plugin that you need to install. But for since 3.10, then we are going to kind of out of box being supported by PyTorch on this quick exchange. Yeah.
Got it. Okay, makes sense. Thank you.
Yeah, and also one thing to call is the lower bound, right? The lower bound, the best you can get is 0.1 microsecond. You cannot get lower. You cannot below that, because this is like the Python limit that you can get. Yeah.
So this the 0.1. This is just like PyBind, or this is the vtable lookup that you referred to. The
0.1 is just Python call. Like even if you don't do PyBind, you do a zero abstraction, just Python C extension. You call a function through in Python is 0.1.
I see. And sorry for putting you on the spot. But do you expect this is a hard constraint on the Python side, or do you also expect with further investments there?
That's a great question. The honest answer is I don't know. So this is only like the benchmark number I see, right? So, and also, I would envision it can be very hard to get through, mainly because even if it's not external function call, like even if you are just doing like a Python function, like native Python function call, it's also roughly at the same level. So like the interpret overhead, I think is really hard to kind of like get below that. And 0.1 microsecond is 100 nanosecond, right? So it's already like very, very, very close to metals. So roughly, if I'm to give everybody a sense, if you do like if condition memory lookup or atomic load operation in native, it's roughly 10 nanoseconds, right? So if you do 10 of that, you kind of get into 0.1. So like it's really easy to get into 0.1.
I see. Okay.
When you're looking at host overhead here, yeah.
Okay. Maybe when you finish your talk, I'm sort of curious. It sounds like you have a lot of these numbers in your head. So
yes, I have a slide about this. I have a slide.
Oh, so okay, wonderful. Okay.
I would definitely love to get back to this. Yeah. So, yes. So I do want to give everybody a bit more color, right, on what exactly look like in the ABI, because I talk about hey, this is a TVM FFI ABI. What exactly look like, right? So we do design TVM FFI ABI to be a minimum thing, so that you don't need a compiler to target it. You don't need to use libraries. You can just hand wire your function and expose it in a TVM FFI ABI format. So here's what it looks like. Say I want to define a function called add1, right? So that's going to add, like take a tensor, I'm going to add a value 1 to it. So here's the signature you want to expose. So you want to expose a function with a C symbol that's prefixed by underscore TVM FFI, add1C, right? And it's going to contain a handle field. The handle field, you can ignore that for now, because usually it's only used by closures. We are not using closures in this particular example. You have arguments. That's going to be on stack values of list of arguments. The number of arguments are being passed into that pointer, and the result, this is going to be used to pass return values. We're also not going to use result in this particular example. Right? So you can find that this is a mechanism called type erasure, because because normally if you have a function of a lot of arguments, right, they need to have different function signature, but we want to erase all the types of the FFI function onto this common unified signature. So this is only one signature. Independent of number of arguments, what types you call, they're always going to follow this particular signature. And then this TVM FFI any is what we call tag union object. I'm going to kind of dive into detail in the next slide on what it's like. But effectively, it is arguments that can recall what type of each of argument is, what exactly value of each argument. And effectively, this is the signature that allows us to be able to express any function with any number of arguments, right? So what we'll be able to do is say, I want to implement add1 function. all I need to do is I'm going to iterate over these arguments. I know that I need 2 arguments, so I'm going to have argument 0, argument 1. I'm going to read that. In this case, I do follow a convention. So this is a read DL tensor convention that I can take argument values, and then I'm going to check each of the value have a type index I can check. So I'm going to check, okay, if this type index matches the DL tensor pointer, right? If it's a DL tensor pointers, I know that after value index, there's a pointer field that I can read the DL tensor from, and I'm going to return 0, which means that it's a successful read. Alternatively, there's another tensor type called TVM FFI tensor that's a in reference counted object. So when the user passing tensors, there are 2 kind of ways they can pass onto a TVM FFI ABI function. And if it doesn't match, what I'm going to do is I'm going to use this set error to set an error message to be raised back to Python. I'm going to return -1. So the calling convention says that, for any of the FFI function add 1c, if you return 0, it means that the function successfully returns without error. But if I have if I return -1, right? In this case, if I have a type error, in this case, actually this should be a type error instead of value error, then I will be able to return -1 to my callers, and then our handling mechanism is going to kind of look into -1, fetch the right kind of exceptions, throw the right kind of Python exception back with this error message, expect the tensor input, right, to the Python caller side. So effectively, it's nothing magic, right? It's very kind of like it's kind of just defines a common convention or what it means to call into our functions. And all you need to do is you kind of iterate through our parameters, read your type code, check if the type code is right, and decode the right kind of data structure onto the field you need. So once we have this DL tensor things, we also have these functions like get environment get stream. So this is a function that allows us to be able to get the torch stream from PyTorch environment, and then all I need to do is I can perform computation here, right? So this is exactly one example I really hand wired just in C. Like this is if you save it to a C file. We do have this example in TVM FFI website. So in the future, if afterwards, you are more than welcome to go and hand wire your own TVM FFI function, right? And you can just invoke compilers to compile it. You can just use gcc -o mylib.so. It's going to give you a shared libraries, and then this library you will be able to load it back using TVM FFI load module and call it using the same mechanism. It's the same as how you call flash infer. It's the same how you call QDSO compiled function, right? So that's what I mean by ABI convention, right? We are just defining what a function should look like, and then you are just following this convention. As long as your function you define your function following these conventions, we can build the surrounding mechanisms to be able to call into it, to be able to kind of build this as a library, so package it, and so on. So that's like really the key here, right? And effectively, if I build a DSO compiler, I don't have to hand wire this add 1 logic, right? My DSO compiler is going to generate logic, both this part of logic, but also this kind of the function signature reading and error checking logic is also going to be generated by DSO. But it's really important and useful to just hand wire your own FFI function to get a sense of what it looks like. And as a matter of fact, our C++ bindings of that is exactly kind of building on top of this hand wiring feature, right? To allow us to give you a very convenient way to just use a micron to export a C++ function as a TVM FFI compatible function. Yeah. So so this is just like a zoomed in view, right? So this is a TVM FFI C ABI that contains arguments, and each of arguments is a continuous any data structure that I'm going to explain next slide. That's going to contain a type index field in its head, and the additional field that contains things like what is the exact pointers you are looking into, right? And we also have a return value that allows you to be able to return a value onto the caller side. And this ABI convention is being documented as a stable standard. So our goal is really we are not going to change it. Very unlikely to change it in the future, and even if change it, we're going to do strict versioning, right? So that people are able to rely on it. As a matter of fact, Flash Info and our libraries are already relying on it for doing their function exchange. So there are a few key data structure here. The first data structure is TVM for any. So this is really the main data structure where, this is really the main data structure we are looking at here. And so that represents effectively most of the data that we will be able to pass around the functions boundaries. So the first field of any is type index. That's going to contain different types that indicate different types. It includes things like integer, float, string bytes, tensor data structure. We do allow pass FFI function also as FFI any. So you can pass in closures and callbacks. We also have mechanism to be able to convert Python function onto FFI compatible ABI. So you will be able to pass a Python callback onto your low-level C++ function, for example, using this mechanism. There's also device and D type. And also we support a bit of container types like array and map so that you will be able to pass in tuples and so on onto your backend. And the second part, you can ignore this 4 bytes part here. This is just zero pointing and a bit of them used by small string that you can ignore for now. The second part are just these additional field. For example, if I want to pass an integer, what I'm going to do is I'm going to store type index as TVM int. I'm going to store the vint64 field as the integer value, right? That's how I'm going to pass integer values across FFI boundary. If I'm going to pass in a PyTorch tensor, however, I'm going to store this field. Usually, it's going to contain FFI tensor field in there that's being converted by the front-end Python bindings, and we have a v-object pointer that points on heap object. That's reference counted, and that kind of effectively correspond to the DL-pack data structure that you have in there. So you kind of get the idea, right? So it's nothing magic. It's also called tagged union data structure in programming languages, right? So TVM FFI any is just a standard tag union object that represents kind of like different values being passed around. We do have this TVM FFI object. And that allows us to do custom object extension. That means that we will be able to introduce customized object other than the building object that we build in onto the system, because we do recognize this very important to be able to introduce additional data types if needed. So TVM FFI object. So this is kind of like a standard reference counted object. So we have this combined reference counter. Actually, design was borrowing from PyTorch that contains a reference counter that kind of combines both strong and weak reference pointers. We have a type index that's kind of the same as the TVM FFI any index that allows us to recognize what type it is. We have a customized deleter function. This is very important, and that allows us to be able to define how you delete object. This deleter contains flags, so this flags mainly be used by doing like both weak and strong deletions. But the idea is that for any object we allocated from TVM FFI, it's going to carry its own customized deleter. That means that it allows us to be able to allocate objects from different languages. For example, if you allocate one object from Rust, and you pass it to C++, right? So when you deallocate object, you wouldn't be able to know that you want to call the Rust deallocator to be able to deallocate that object correctly, right? So if you don't have the custom deleters, this is kind of impossible. You also start to see problems like, say, if you have different DLLs, even in C++, maybe you have like different deletion logics for different of them. So the custom deleter really makes sure that when we recycle the object, we will be able to call the right deleter, so that it gives you ability to be able to allocate your custom object in different languages and pass around while be able to recycle them very correctly. And also, because we have a type index, we have a dynamically allocated object type table so that object counts can grow if needed to support custom objects. We do find for almost all the needs, we don't have to make use of custom object, but for certain advanced need, there are use cases on supporting like a dynamic objects that you can register on the fly and you can introduce for your use cases. So this is it, right? So it's nothing magic in a sense that we kind of if you feel like it's so simple, that's the point, right? We really want it to be minimal, and the idea is that as long as you are able to define your function and exposing this convention, we can build a function around it, right? So it's so simple and minimal, so that you can just hand wire it, and then we will be able to build DSO compiler that generate this boilerplate for us, right? So it operates at close to mental level, right? So you almost don't need any language support, right? So we do have a few need of this runtime function like set errors, but it's really minimal. Like as a result, the lib TVM FFI is like less than one megabytes. It can be further minimized. That gives you covering like common data types, and it gives you a very ultra low overhead, because effectively when you're passing around, you're just reading pointers and doing in memory things. You are not invoking any interpreters or virtual machine or so on. I also truly believe it's a changing mindset, right? In how we think about interoperabilities on languages, because traditionally, when we write code, we think about we always write code in one languages, and then we worry about bindings, right? We use binding generator to generate bindings to another language if needed. But I do believe, like for the case of machine learning systems, given that there is a need for so many things to interoperate with each other, it's very useful for every DSOs and libraries to think about interoperability as a first class, so that you can always expose your function following these same ABI conventions. As a result, we kind of turn this many-to-many interoperability problems into many interopt with common ABI conventions, and then kind of many-to-one, one-to-many problem, where effectively we can have a lot of the out-of-box interoperabilities across it, right? So this is, I do think, a change of mindset that can really benefit the entire community in here. So now we introduced TVM FFI ABIs, right? So let's talk about what are the cool things we can do with these ABIs and the current applications. One of the things that we already alluded before is that we can use it to ship one library for almost all the machine learning system needs. So say you have a library or DSO or AI agent, I could expose my functions, right? Again, we are not trying to replace your DSOs, agent, or libraries, because the DSOs, agent, libraries, you are doing all the magic of writing the fast performing things. We're just trying to provide this common standard so that you can expose your function too. So you can expose your mylib.so following this ABI convention that we just introduced. And then it's going to minimally depend on libtvm.so or .a, or depending on whether or not you want a static bundle, right? So once you have this, you will be able to ship it onto different environments. On different environments, we do have a different Python version dependent TVM FFI packages that knows how to interact from Python to this ABI, right? So as a result, you just need to pip install Apache TVM FFI, and on these platforms, you will be able to run across PyTorch, JAX, NumPy versions. This particular .so is not going to depend on any of them, right? So because the version dependency is being handled by this particular version dependent libraries in the Apache TVM FFI. Or you can say, I only want to call that from C++, right? Then you don't need Python dependencies. You can directly link it through XA callback or inference engines. We also have experimental Rust support that you will be able to directly call those functions from Rust, and which is kind of quite fun as an exercise. So I'm going to talk about some of the current usages and also some of future integrations. This is kind of presenting on behalf of many amazing collaborators. This really thanks to them, right, on building some of the current support and integrations, and this is a growing list. So we are seeing a lot of momentum both in NVIDIA and in general open source communities. The first one is, of course, FlashInfer library. So FlashInfer is this open source library that we built for supporting high performance LM inference. And since 0.4.0, we started to ship TVM FFI as a stable ABI interface for all our Python kernel exposures. We also support AOT wells, so that you will be able to package some of the wells like FlashInfer.samples, and you will be able to use the mechanism to run it in PyTorch and run in non-Python environment. And we do have specific use cases. For example, more recently, we have use cases on bringing up JAX-based inference frameworks that some of our customers is interested in, right? So using this mechanism, because we have like this ABI that we can expose to different environments.
Sorry, Chen, just to make sure I understand this. So let's say a kernel DSL does not have an AOT story. You can give it an AOT story?
That's true. Yeah. Effectively, a kernel DSL, as long as able to, expose your function that wires up in this TVM FFI ABI format, right? And then effectively, that's the AOT story that they can have. So they will be able to directly kind of like load this because all these mechanisms, right? Loading modules, invoking, passing C++ types, and all these other things are supported out of the box. Yeah.
Interesting. But there's still an assumption here that like the hardware on which you created this binary is the same as the hardware that you're running on, right? Because like let's say for example, like your kernel DSL is using some TCE Gen 05 intrinsics, because like things like QDSL, per my understanding, won't work on anything except the Blackwell GPUs.
We are not going to solve the portability problem. Right? We're only going to solve that's a harder problem to solve, right? You kind of need a JIT or other or even JIT wouldn't work because QDSL is not really portable across hardwares, right? So, but we're only going to solve the kind of like a minor problem, I would say, but still important, or making sure that you will be able to run agnostically without Python, for example. You will be able to have a ABI that you will be able, if you want to program C++ or Rust or other languages against, right? That's an interface you can expose. So that's only part of a problem we solve, but it does help on the AOT story here. Yeah. So and on the agent side, right? So we do take very heavy inspiration from awesome loading line in Torch. So there is this TVM FFI CPU.loading line function that allows you to directly compile a loading line a Python module in Python. And it's very useful for a coding agent to generate kernel in a loop. And more recently, we also support a function called building line that allows you to take this same function signature, but gives you a .o or .so file that allows you to ship AOT compile libraries, because we do find in certain cases there's a need to bundle your agent-generated code to your C++ or other applications, right? So it's kind of like a path to ship reasonably standardized kernels for agents. And we kind of recently moved our flashing for a bench agent-generated interface towards this interface, and it's still work in progress. So for those who don't know, flashing for bench is this kind of like an agentic benchmark that we build on trying to both curating the set of workloads that we think are very important for our inference, as well as trying to take those workload trays and be able to generate a library and apply it in inference engine. In particular, in this case, we have a first-class flashing for supporting here. And we also have recent MLSys competitions on some of the flashing for kernel challenges. And however, one of the key questions we always ask, now that AI agent generate a good kernel, right, how do I deploy it? So in this case, what we find that TVM FFI serves a very natural convention, so that we'll be able to take some of those functions and trying to kind of bundle them and expose in TVM FFI ABI conventions, so that they can then be consumed by some of the different deployment environments in here. And there are like effectively a solution that gives you ability to be able to support both different libraries, languages, and some of the compiler caching supporting here. So in this particular case, a flexible bench will also try to expose something that contains TVM based modules, as well as some metadata, so that people will be able to read from. Actually, in this case, a lot of cases for agents. Right? Agents will be able to read those metadata and hopefully knows how to organize those exported modules into a end-to-end application of interest. We do have JAX support. So in this particular case, JAX do have this. So if you want to call a function effective from JAX, you don't really want to use Python, as a matter of fact, because JAX kind of compiles this code using XLA graph. So ideally, you want to kind of bundle your executions, your kernels onto XLA graph, and that was like usually a tedious problem that you kind of need to have build there's its own bindings called JAX FFI to be able to kind of bind a function to JAX. So we have this mini package called JAX TVM FFI. So in this particular case, it's kind of motivated by some of the use cases we face at NVIDIA. So you will be able to load in a TVM FFI modules that gives you a TVM FFI functions, and this JAX TVM FFI will serve as a bridge. So it's going to bridge the TVM FFI function to JAX FFI and register it as a JAX callback in the environment, and then you will be able to use JAX FFI call directly to call into this kernel. So And one thing that I really want to emphasize is this really composable, right? So this particular load module add one cool.so, you don't need to worry about whether or not it's a kernel coming from FlashInfer or kernel coming from QDSO or kernel that we hand wired, right? So effectively, as long as it follows the same ABI conventions, this JAX API is going to be able to pick it up, and you will be able to call into your call it from JAX if needed. More recently, because this FFI ABI convention is so minimal, right? It's actually quite ideal to build JIT compilers, because all you need to do is you have some ability to either cogen or stitching up. In certain cases, stitching up just CUDA-C code, right? And then use that as an exposure layer. So more recently, SGLang adopted TVM FFI ABI as this JIT exposure. So a lot of the Elm inference engine are moving towards JIT, because JIT gives you ability to be able to quickly prototype your kernel without rebuilding your entire project, right? You just JIT your kernels, and you can hook it into your inference engine. And TVM FFI is a kind of like an ideal minimum interface that you can use to be able to JIT a kernel. Then you can use the same function like load modules, passing PyTorch tensors, doing all the tests you need, right? So it is an ABI that SGLang now using JIT to target today. And of course, last but not least, I think one of the most exciting things we've been working on in the last year is QDSO integration. QDSO is great; it gives the ability to be able to write state-of-art kernels on Python out of box, right? However, when we started to build QDSO, we do hear a lot of complaints. For example, one of the complaints is that if you write QDSO kernel, you have to use from the OPAC, right, to convert from PyTorch tensor to QTensor before you are able to pass your tensors onto the kernel. And also, unfortunately, some of the conversion is not fast. What we find out is that if you do the from the OPAC and also do the attribute calls and launch the kernels, a lot of cases, the time we spend on the host side, right, not even just getting to the fun part, is kind of beyond, in a lot of cases, sometimes it usually can be up to 20 microseconds or more, right? So in a lot of cases, for example, a simple IMS norm kernel is getting close like 2 microseconds. So really the host OS ahead is kind of killing a lot of our performance. And also there are, like, even when we use from the OPAC, there are certain things that are not very out-of-box supported. For example, we know that for PyTorch libraries, we do have this assumption that if you have a kernel, you can pass in tensors, right? You can pass in tensor from different devices. Like I can pass in tensor from GPU 1, and it's going to automatically launch on GPU 1. However, in QDSO, originally, if you just pass in tensor in GPU 1, so you kind of need to manually do CUDA set device to be able to set your device context to GPU 1 before you're able to launch it, right? So there are kind of all these additional things you kind of have to do around. And another thing that we have to do around is attribute checking. So because a lot of cases, when you build your kernels, you kind of assume that, hey, because you want to write kernel efficiently, you kind of assume that, hey, this particular shape should be multiple of 16, for example, right? My data alignment should be multiple of how many elements, but not always the input data is going to satisfy that. So what we do today is we are going to try to write checks in Python, right? You want to assert my shape is multiple of 16s, my device is on GPU 0, and so on. Otherwise, if you don't have these checks, you're going to stack for it in a lot of cases, and that's not fun. Right? So we think, and one last thing that's actually was not commonly talked about is actually QDSO itself also have an issue of how do we define AOT, because we kind of wanted to be able to ship AOT kernels for people who want to deploy it onto non-Python environment. But at a low level, actually, when we do parameter passing, the ABI, the way we pass tensors can change when we, whether or not the tensor is dynamic, have static shape, and so on, because we kind of want to optimize for efficiency. But that's not very ideal for users, because we want users to be able to pass in one thing, right? Regardless of whether or not how they tune their kernel. So all this leads to the motivation of hey, can we bring a TVM FFI ABI exposure of a QDSO? So that's one of the effort we have been working very hard on since last year. Is now shipped as a standard feature in QDSO. So say you have a Qt kernels, what you can do is you can do qcompile, and you can have this option. Right now it's opt-in because it's the first release that support TVM FFI. We are actively discussing, do we want to be able to make it a default? But in general, you should be able to directly enable it by this explicit flag. So once you have this ABI conventions, what you now be able to do is, instead of doing from DL pack and then passing tensors, you will be able to directly pass in torch tensors to this kernel, right? So this particular L1 kernel effectively is the same TVM FFI function that we just showed before. Like all those functions that being compiled are flashing first or hand wild, except in this case, it's the QDSO compiler that hand wiling all these surrounding shims for you, right? So that you are going to get this L1 kernel that you can further use. So because TVM FFI naturally allows you to the AOT, so now you will be able to compile these L1 kernels, and there is ability for us to be able to export this kernel onto a shared libraries, or we can also support it to export it to a .o file that you can just bundle everything together in a single application if you don't want shared library in here. And this particular export to library support allows us to be able to, again, have this add1.so, and you will be able to load it back in Python and run it in PyTorch, and you will be able to use the same mechanism in JAX TVM FFI, right? So again, in this particular case, it doesn't matter if this add1.so come from QDSO or another DSO. For example, we're going to show Thailand as the next example. And in theory, if Thailand is able to expose the same add1.so, or if you write it CUDA-C, but hand-wired in TVM FFI format, the way you kind of make use of it is going to be the same, because they kind of follow the same interface convention, right? That's a nice part of it. So that, at least in every framework, as long as you know how to invoke onto TVM FFI functions, then you kind of opens the doors to all the DSOs, right? That supports the conventions. In the same spirit, as long as the DSO exposes a function signature that follows the TVM FFI ABI conventions, it opens the doors of integrations onto all the frameworks that supports invoking onto TVM FFI ABI convention, which is kind of growing. We have like PyTorch support, JAX, we have native C++ support, and we're working on actively on TensorRT support to be able to call into FFI compatible function in TensorRT. So this is how you use it in AOT, right? So so this slide promise Mark. So we are optimizing very hard on the host overhead, and throughout this process we do find a lot of interesting numbers that I think everyone should know about, and this like there's this like latest number every programmer should know, right? That's a famous number from Jeff Ding and so on, and this like a GPU kernel version. So here are the numbers that I think is important to keep in mind. So first of all, it's very important to know that what is our limit in Python, right? So in Python environment, if you do like Python to native C function invocations, roughly 0.1 microsecond today. By the way, all these numbers assumes a hot loop. So that means that usually you kind of want to warm up your program. You're going to repeatedly looping over the same functions. I know that it's not always the case on certain environments, like the cache itself can be a different issue that we want to solve. But on this is the kind of limit on a hot loop, right? So in this case, if you do Python to C native function invocations, it's going to be 0.1 microsecond. So that really limits the things you can do in Python, right? So think about if you want to write Python attribute checks. Say if you have a function, right, that contains 3 parameters. For each parameter, I need to check shape constraints. Usually shape constraints have a few dimensions, right? I also want to check alignment constraints. And that can easily end up with maybe 5 or 10 checks. So if you have 10 checks, very likely all those checks added up together is going to blow up to 1 microsecond or 2 microseconds, because these are Python ifs. Each of a Python if roughly is going to be 0.1 microsecond at least, right? And also you need to do attribute access. Like I need to do a.shape0, and that's like a.shape is attribute access, and attribute access itself is a Python function invocation that's going to cost you 0.1 microsecond. Shape0. Get item 0 is another Python function access, right? That's going to cost you another 0.1 microsecond. So even if you just write something like if a.shape0 equal 0, equal 128, right? So say I have a kernel that specialized shape 0 to 128. This particular line can already add you up to like a few, maybe less than 1 microsecond, but I think definitely 0.1, around 0.5, because you kind of need to do attribute loadings, get item, right? Then comparison, right? So at least 3 operations. So at least 0.3 microsecond in here. In comparisons, if you have a native compiled code, like say I have like a data structure A that sits in memory, C struct, and I do A.shape 0, that's roughly like a 1 memory lookup. It's roughly going to cost you 2 to 10 nanoseconds in here, if it's like a non-automatic access, right? So there is a gap from compiled code to Python access in here. But of course, we want Python because of flexibility, right? So it's also important to understand that when you launch a kernel, if you do like just do a CUDA kernel launch, like without any additional things, and the kernel say is no op, today the driver overhead is roughly around 1 microsecond. And then a typical low latency Blackwell kernel, for example, if you take IMS norm kernel on Blackwell, it's roughly going to take you 2 to 3 microseconds. And the way that CUDA kernel works, right, is that usually when you launch, because we are kind of eagerly launch kernels, right? So we have K0 on the host side, and then you have host side K1, and then you have like device side K0, device side K1, right? So as long as your host cost is smaller than the device cost, then roughly the cost can be hidden behind the kernel launch, right? This is, by the way, this is eager cost. So this is the cost you pay when you launch PyTorch eager, right? So that's why actually CUDA graph is really important, and this CUDA graph helps us to eliminate a lot of these costs, right? So if you have like a 3 function or 4 functions that launches together, you use CUDA graph capture and you use then rerun, all this overhead are going to be eliminated. So we're really talking about eager overhead. But ego overhead is also being very important, we believe, because the reason why PyTorch is so successful is one reason is because eager, right? And it's also very nice to be able to kind of have kernels that we can eagerly invoke and so on. So it's really important to optimize for those overhead. And if you look at this, right, you can roughly say that ideally we want to get our kernel launch overhead to be around 2 to 3 microsecond level, your host overhead, so that you will be able to hide behind the launching cost. The reality today is that a lot of cases, the host overhead for a lot of DSOs can blow up to 20 to 30 microseconds in many cases, because a lot of costs are in Python, to say native function cost and a few other reasons, right? So our one of the is very interesting. When we start to work on TVM, we kind of asked as a challenge that can we get down the eager launching overhead down so that it can be reasonably hidden behind the scene. And the answer is kind of obvious, right? You kind of want to move a lot of the Python related things, which cost you 0.1 microsecond, onto the native land, so that it wouldn't cost you as much, right? And so we kind of set out to do that. And when you compile DSL function, roughly it kind of like a breakdown onto several parts. So you have your arguments in Python. These are like a torch data structure in memory. In TVM FFI, we kind of gives you this TVM FFI function in Python that have ability to be able to convert those Python arguments onto the ABI convention. And this layer is heavily optimized. So today we kind of get it down to about 0.4 microsecond. And if necessary, we can get it down even further to 0.3 microsecond level. So this is kind of reasonably optimized. And then another thing we do is we move almost all the constraint checks and value packs that otherwise previously in Python onto below. This is now compiled code. So this is compiled code. And previously, each of a track cost you around 0.5 microsecond, but now it's around 10 nanoseconds per track. So you're almost getting those tracks for free. And then we're going to launch kernels, right? That's going to cost you like 1 to 2 microsecond overhead. So as a result, if you use TVM FFI today through the QDSO functions, you can roughly find that the host overhead is around about like a 1 to 2 microsecond. If you kind of benchmark an empty queued kernel in a hot loop using TVM FFI, whereas if you don't use TVM FFI, it's going to blow up to about 10 microsecond in a lot of cases, or even more as you have more arguments. So it really gives you kind of a huge saving in terms of like a host launching overhead. And this is what we are really proud of. Besides the interoperability, right? We kind of set out to do this not for the host launching efficiencies, because we do think interoperability is really important. But in the end, we found that because we can standardize this layer, it helps us a lot on kind of reducing some of the host launching overhead as well.
So, Tianqi, I want to ask you one question. So this is like a mix of a technical and maybe more of a product question, but like I've often had people say something along the lines of like, oh, thinking about overhead is too hard, just CUDA graph everything. Like what's sort of been your response to claims like that?
That's a great point, right? So yeah, first of all, people should be aware of CUDA graph. People should be using CUDA graph. That you should definitely use it if it's possible for your scenario. On the other hand, CUDA graph doesn't come without its own problem, right? So in a sense, for example, CUDA graph do not support dynamic shape in a lot of cases, right? And also, if you have data-dependent control flow and so on, it's almost impossible to capture CUDA graph. Maybe you can do piecewise CUDA graph. That's another kind of possibilities. I do think that's important to kind of improve on all fronts. So where an eager overhead, if you can reduce it, it's certainly save a lot of things. For example, in a lot of cases, when we do kernel benchmarking, right, it's much easier to say, I compile kernel, don't worry about CUDA graph, you just benchmark it. And having ability to be able to do that, I think is great. Yeah. And also, I do think that it's also a matter of kind of like arm.law coming in and out, right? So in a lot of cases, for example, as we start to kind of like bring down the host overhead, it's not only for kernels in certain sense, right? For example, one example is like this project called XGramma that we built for like a structured decoding, right? So in that case, we are kind of building like grammar engines where we will be able to generate masks for language model outputs. Right? These are CPU functions that are also need to invoke, and there's also kind of like a invocation overhead across those libraries. So I do think that generally it's good to kind of push all the front when possible. This being said, I do think CUDA graph is a very important solution, and we do want to be able to make use of that when possible. Yeah.
Yeah. Okay. Cool.
Yeah. So this is, and actually, one thing we do find is at least today, if we can get things down to like a 1 to 2 microsecond level, at least on Blackwell, we don't yet have to use CUDA graph, and maybe on the future generations we still need to do more work. But definitely it is something that today we can make eager great again, or great, right? Still great for our use cases. Okay, so that's like how QDSL do it. But in general, in case you want to write your own JIT compiler, right? So you can leverage some of the existing APIs to kind of build up your function in Python. So TVM FFI provide two functions. One is called from my pack function call, and another from externc. So basically, these two functions are just taking log function pointers that follows TVM FFI APIs. It doesn't matter where you get log function pointer. For example, you can get it from DL open. You can use your own OCJIT execution engines to JIT execute, to JIT build that particular function, and you point your function pointers to those functions. It's going to give you a Python function that follows the same TVM FFI conventions. You can pass in torch tensors onto it, right? So it's a very useful modular APIs that you can use to construct FFI function. It is the API that actually QDSL compiler used to construct the related functions that and expose them in Python. One thing that we are really proud of is we really allows us to be able to throw the right kind of Python exceptions instead of segfault, right? So in general, if you run Python checks, there can be a lot of the overhead if you write your checks in Python. But we do want to make sure our kernel is robust. So we want to be able to check D shape, D type alignments, and so on. And compile check are great for this. So each of a compile check roughly gives you 10 nanosecond level, right? So it's almost free, and usually you can generate about 10 or 20 of them, and still kind of like getting below the getting below like a 0.1 overhead in general. And the mechanism we use is we have this runtime function called TVM FFI set error raised from CSTR. So you can pass in streams that contains the exception you want to throw and error messages that you want to throw, right? So effectively, this is a very convenient runtime function that compilers, and if you handwire, you can use it to kind of throw the right kind of errors for you. And QDSO compiler will generate all these checks for you, so you don't have to write the checks. So here's how it works. Say you have a cute kernel, you can declare a cute symbolic integer n in here. That's my shape value, and I want to say this is divisible by 16, right? So this is a symbolic integer that divisible by 16. Then we can make fake tensors that declares, what kind of tensor argument I need to pass. These are tensor arguments that's supposed to take FP32, right? And then there are two shapes n and n here. We also assume that the data aligns to 16 bytes. So these are all the constraints we declare in the Qt interface. Remember that these two n's are the same, and that means that the two inputs must have the same length, right? So in this case, the vector add, these two a and b should share the same input length in here. And if you're smart enough, you might figure out that I can also use it to declare a matrix multiplication constraint. Right? Effectively, that means I can declare n and k, and the k of the two matrices need to be kind of matched against each other. So once you have this, you can compile. And this compiled function is going to readily come with all the checks that checks divisibility constraint, checks the shape equivalence, and checks the data alignment assumptions. And here are some examples, right? So these are examples in the official QDSO document. So if you go to QDSO compile to TVM FFI ABI guide, you can find those snippets. You can directly copy and run them. So say if you compile this function, right? And this is the compiled add one. If I pass in a function, say this is a torch tensor, but I pass in 1, which is an integer as a second argument, it's going to throw the following error messages. So you're going to say a message called type error, and this is the exact message. Actually, this is the exact error message that you're going to see on screen. So it's going to say, here's a function that expects this signature, right? This n1, n1, and the mismatch type is argument 1 because we are 0 indexing, and it's expected tensor type, right? So it's kind of very clear error message tells you, okay, you're passing a wrong argument in here. It also gives you a shape equality check. So say if I gives you A and I give you B, and I'm going to slice it to in this case, actually, B should be bigger. So say 256, I'm going to slice it to like 124, and it's going to report you this error message, right? You're going to say, okay, this B dot shape 0 mismatched, and it's expected to match A dot shape 0, right? So it will tell you that, okay, the shape should match the particular constraint in here. It also have divisibility check. So if you pass in two tensors that's of length 126, it's going to tell you that, okay, this particular A dot shape 0 is going to be expected to be divisible by 60, right? So all those error messages are being kind of thrown onto Python using the same mechanism called TVM FFI set error raise, right? You can imagine that our compiler is going to generate all those checks and call onto the right set error raised function correctly, right? As a matter of fact, we have a different function called set error raise from parts, so that we can divide up these error messages into several parts and try to compress the parts a bit. So for example, this particular function signature is being stored once in the compile code, so that overall compiled binary is minimum while containing all the error messages. And we also have alignment checks. So in this case, if you're passing a line on a line address, which is very common, like you have a tensor, you slice it a bit, then you get an address that's not aligned. In this case, it's going to tell you that, okay, you are passing a tensor, but really you want to align or contiguous address, right? So it's very nice error messages that gives you ability to have the right error, right? Instead of stay at a stack fault and trying to figure out what's going on. So we are really proud of these additional improvements. These are really free. Like actually, if you turn on TVM FFI, enable TVM FFI, it's going to reduce your host overhead, and it's going to have these additional compile checks that kind of guard against all those misuse. Additionally, also it's not shown in the slide. We do have this automatic device support as well. So if you, for example, passing torch tensors from CUDA 1, GPU 1, it's going to automatically switch the device to GPU 1 and launch the kernel on GPU 1 for you, right? So it gives you a very streamlined PyTorch experience that you expect from a normal PyTorch operator in here. Okay, so at a high level, if you want to minimize your host overhead in QDSOs, here are the things you want to do, right? First of all, you want to compile the kernel with key value enabled. Try to declare your shape constraint as much as possible using fake tensor, and don't try to write your own checks. Try to make use of shape constraint features there. Directly passing PyTorch tensors, you don't want to do explicit DLPAC conversion anymore. There's a stream passing mechanism that allows us to directly passing PyTorch streams, and then rely on runtime compiled argument validation, so that we will give you performant fast compile checks. And there are like a latest document you can check out in here.
Tianqi, can we go to the previous slide? Just two questions here. So the first one is like within PyTorch, I think we often typically get like some security researchers telling us like, oh, there's like an out of bounds error on this kernel. But like, our argument back is like, well, like, this would kill performance. At least like your experience is like that it's fine to have some of these checks in native code, or just want to double check here.
I think at least for the example we use so far, it's okay. Like native checks in our benchmark, it's not free, right? It's 10 nanoseconds. So if you have 100 of them, then that's like microsecond. So, but if your kernel is about 1 microsecond, you can have 10 of them without impacting the host overhead, right? And also, it's our internal discussions. We do discuss that maybe we can also try to kind of like streamline it a bit further, so that you could have a unsafe mode. Like you can have a pre-checked kernel that run all the checks, and then in the future rounds, you just you skip all the checks if needed. Yeah. A short answer is if you have 10 compile checks, I think it's okay. Yeah.
Right. Oh, so one thing I found interesting in the previous Qt example you had, if you go one slide back, I think you had like both cements here and then like fake tensors. And this is terminology I think that the Torch compiler team like uses like quite a bit. I was wondering, could you maybe just explain it a bit more to the audience, like why these two concepts are important?
Yeah, so the reason is that when we compile the function, right, so we don't really want to realize the tensors, because they are for several reasons. For example, the first reason is that when you have a real tensor that gets into a compiler, you get concrete shapes like 4x4, right? But your real intention maybe, I want this kernel to work not only for 4x4, but also 4x8 or 4x16. As a result, you want to really declare your tensor as 4x(n), right? Where n is divisible by 4, for example. That's a better way to declare your thing. So that's why we need to have a CMIT that kind of like declare a symbolic constraint of it, right? Another thing that CMIT is great at is gives you symbolic equality constraints. Like for example, if you have n and n in here, it kind of you know that these two need to match each other, right? The fake tensor kind of also serves that purpose. It gives you the ability to be able to compile the function without having to allocate a tensor for that function, right? So this is useful, for example, in cross compilation scenario where, say you want to compile for a Blackwell kernel, and in theory, you should be able to even cross compile a device that don't have Blackwell, right? So because you just need to declare your fake tensors, then you will be able to compile that function. So that's really a mechanism for us to be able to declare the signature of the function and the constraint of a function to the compiler, so the compiler can take that and generate the right checks for you. Yeah.
Right. Yeah. Very helpful. Thank you.
Okay. So it's not only on QDSL, right? So here's another example of another DSL called Thailand that leverages TVM FFI. As a matter of fact, because Thailand kind of natively integrated with TVM, so it not only used TVM FFI for runtime, but it's also used for compiler integrations. That's a separate story. But in general, it's kind of similar. Like Thailand also find that after using TVM FFI, this on H800, they find about 3x reductions in terms of their CPU runtime overhead, but also it kind of greatly reduced their compile time overhead in this case, because very likely it's because when you generate a kernel that target TVM FFI ABI is so simple, so that kind of compile overhead of that ABI is reasonably reduced. So that's also great news for Thailand in general, and all the same mechanisms that you see today, like loading PyTorch, running JAX, calling from C++, Rust, right? All those mechanisms kind of also works for Thailand as long as they are exposing the same ABI in here. Okay, so that's the last slide. So we are really exciting time of building machine learning systems. I think everybody can be their own, and thanks to AI agent, everybody can build great momentums and great ideas, right? And one thing we really want to enable here is not only to give everybody ability to realize their dream, but also be able to easily interact and connect with each other. So Team FFI is not really meant to be another framework, right? It's meant to be a common convention, minimum one, that we hope to bridge everything together. we do hope to bring this open ABI convention and standard. So this open source project on the Apache Software Foundations. You are more than welcome to check out the GitHub repo here, and we definitely love your input and contribution as well. And in a lot of cases, you don't necessarily to directly use it, right? You can find that the DSL compilers and other frameworks are kind of already out-of-box integrated with it. So as long as you are indirectly using it, for example, using QDSLs or other mechanisms, you are good. But in case you want to build your own DSLs or JIT compiler or other things that, or in case you want to kind of find a way to AOT interact with certain DSL compiled functions, then this might be your solution. Okay, with that, I'll be more than happy to conclude my talk. Thank you, everyone.
Oh, thank you, Tianqi. Thank you. I guess I see, so a couple of questions in the chat I answered. There's one by Alexander Jang, which is, so some DSLs compile multiple binaries and have internal dispatching logic that depends on runtime parameters. For AOT, will FFI support similar functionalities, or will it be up to the user to support?
That is a great question. So in this case, again, TVM FFI is not defining a compiler, right? So we're not really defining how, we're not dictating how compiler want to expose their functions. It only gives you a mechanism to define how you want to define the exposure boundary. For example, there are two ways you can do it. One way is that you can define your kernel to expose TVM FFI ABIs of the specialized function, and you build a dispatcher on top, right? That's one way. But you can also envision that I can build a C++ based dispatcher inside that calling the FFI, but also expose that function as a FFI function. So that or you can compile that dispatcher, right? So really it's up to the compiler to decide how they want to do it. It's mainly we are providing a mechanism so that you will be able to kind of like build that ABI boundary at the level you want.
Yeah, like the example you showed where like you can just like take in a callback broke my brain a bit, that you can just like have a Python callback and that like just works. Makes a lot of, I think, composability like
exactly.
Like it makes everything click. Okay, I see like another question from Alex. Maybe I'll ask it in a slightly different way. Like Alex is asking, like, could you give an intuition of your project as explained to a newborn? But maybe like maybe I'll ask a slightly better question, which is like, what do you think, like what do you think are sort of like important takeaways like people should have, like as you conclude your thoughts here?
Yeah, I think the important takeaway is that I think in this world, for at least for the FFI project ABR, right, I think it's really important to be minimal and having ability to be even handle wild things, right? And then once you have this minimal thing that everybody can agree upon, it's a very powerful thing that we can build interoperability around. And I think that's really, I do think that's a shifting mindset, right? Originally, people always think about you have to build your project in a single programming language. But I think in the world of machine learning systems, it's increasingly not true, right? You really want to be able to build your things as components and think about interoperability as your first class concern here. Yeah.
And so I guess maybe related to this question, like, do you view TVM FFI as effectively being like somewhat feature complete, and now it's just like mostly about ensuring that everyone adopts it and then you'll move on to the next project? Or do you still think there's sort of like important new features you'd like to build into this?
So I think the core, right, the goal is we want to make sure the core is ABI stable. That's very important, right? So that is why we have a strict versioning policies, and likely we are going to not break backward compatibilities. There might be some surrounding features that we're going to build around, right? But it's not going to kind of impact the current users that much. So I would say it's more like a reasonably stable. There might be feature we want to build around, but we're going to maintain the minimalism mindset, right? So that making sure that this is a stable core that everybody can depend on. Yeah.
All right. Well, I think I don't see any more questions. Tianqi, thank you. It was an honor. Thank you so much for coming on, and please come again anytime you'd like to talk about anything.
Sounds good.
Thank you.
Thanks, everyone. It's a pleasure. Yeah.